Alright, in today's demonstration, I will be showing you how to utilize the eigenfrequency option in the COMSOL multiphysics interface. And we will be studying rigid body modes and resonant frequencies for a cantilever structure utilizing the eigenfrequency study. You could see the summary of this in this page. We will be understanding the angular frequencies, we will visualize the different rigid body modes, and we will estimate the modal mass displacement based on those different resonant frequencies. I will give you an intuition of what all these things are. But before I do that, I will first create a cantilever structure in the COMSOL interface. And the way to do that, like my previous demonstration, I will be utilizing the modal wizard icon. You could use the blank model as well, but the modal wizard helps you set an initial environment, which is helpful if you're just starting out. We will be utilizing the 3D space dimension because our cantilever structure is going to be three-dimensional. What you want to make sure in physics is, once again, you might want to select the solid mechanics solids, which we utilized in our previous demonstration. I'm going to double click on it to add it, and it's going to now prompt me to choose what study I want to do. And for the study, I will be utilizing this time the eigenfrequency study. You don't have to include the stationary study as we did in our previous demonstration, since we're only checking for eigenfrequencies, rigid body modes, resonant frequencies. We are going to select the eigenfrequency study. Yeah. You will give the interface a moment before it opens up a window, and in the geometry you make sure that the length unit is once again set to meters because we are once again creating a macro cantilever beam. And the dimensions of this cantilever beam, as I'm creating it in geometry, you can click on the block option, and that's going to prompt you to create a cuboidal structure. We will use the same dimensions as we used in our previous study, and I'm going to click on build all objects, which is going to create my cantilever beam in free space, right? Now, what you want to make sure before adding constraints is to add material. We will be once again, uh, to add materials again, you click on the materials window and you double click on the add materials section and you simply type structural steel, right? We will use structural steel again for macro cantilevers. Now, a few physical properties of the structural steel I wanted you to remember in the previous demonstration as well is the Young's modulus, which is around 200 megapascals, and you see that the density is around 7,850 kilograms per meter cube. And these two values are very important to theoretically calculate for the resonant frequency of your cantilever beam. Yeah. Um, Now we will continue adding constraints. Now to do that, you click on the physics button, you click on the boundaries, and you select the fixed constraint. A cantilever beam is always fixed in one of its ends, which is what I've emulated here, and you can leave it at that. For the eigenfrequency, you do not have to give a boundary load, because what you're essentially doing in an eigenfrequency study is you're trying to understand how your object vibrates, right? How your object naturally vibrates to give you a better intuition. You want to understand the different ways your object can vibrate in, and the different frequencies at which it's vibrating or displacing naturally. So this is what eigenfrequency analysis basically accomplishes. Let me give you a little bit of intuition into the theory. Now we'll just first make the mesh. This is a tetrahedral mesh. I don't want a tetrahedral mesh, so I go to mesh. I click on the swept mesh button, and I'm going to create an extremely fine mesh in the predefined option. That's going to create a swept mesh, right? Like I told in my previous video, it's always convenient to select a structured mesh as against a unstructured mesh, because a structured mesh gives you better solutions, and you want to use this whenever you can. And for something like this, which is a cuboidal structure, it's almost always convenient to select a structured mesh. Once I've created the mesh, now I'll go ahead and give you some intuition as to what we are doing in today's demonstration. What we are understanding, what we are trying to understand are rigid body modes, right? And to understand rigid body modes, you have to understand what a rigid body is. Now, if any body, which let me create a sphere, right? Any body has multiple points, right? So there's one point here and one point here, and there's going to be a certain distance between those 2 points. We would say that, let's name that distance as d, right? A rigid body is a body such that if I'm going to displace this body somewhere and it's going to go, let's say, over here, the distance between those 2 points are going to be the same, right? Which means between any two given points, there is no deformation when there is going to be an external load. So such bodies are what you would call as rigid bodies, right? So an eigenfrequency or an RBM study is done on rigid bodies. That's the first assumption, right? And what you want to understand here is when an object vibrates. Let's take a cube, all right? There's a number of different ways a cube can vibrate. It can vibrate in the x-axis, it can vibrate in the y-axis, it can vibrate in the z-axis. So there's different translational vibrations this can do, or sometimes it can also rotate torsionally, or it can compress, right? This is called axial. So there's different ways in which a given body can vibrate, right? These are what you would understand in rigid body modes, the different ways in which an object can naturally vibrate. Now, that is the first thing you have to understand, and you have to understand that when these objects are vibrating, they vibrate at certain frequencies. Now, these frequencies are called natural frequencies, or they're also called resonant frequencies, right? Now, these are frequencies at which an object is going to naturally vibrate in a certain direction or in a certain fashion, right? So there is a certain way an object can vibrate and a certain frequency at which the object is going to vibrate in that fashion. Now these things are studied in eigenfrequencies, right? Now these natural frequencies or resonant frequencies at which an object is going to vibrate in is recurrent, right? So it's going to be one frequency, and after a certain range of frequency, at another given frequency, it's going to vibrate in another fashion. So the first frequency is generally what is referred to when people talk about resonant frequencies. They talk about the first mode, and there's going to be a second mode in which the object is going to vibrate in another manner, and after a certain range of frequencies there's a third mode in which the object will vibrate in another fashion, and then it continues, and usually, just considering the six frequencies, the first six resonant frequencies is more than enough to understand 90% of the vibrations of an object, which is naturally happening. And these vibrations are important to consider for structural engineers. These vibrations essentially informs them how much the object is going to vibrate and how the object is going to naturally vibrate. And if they can account for 90% of this, they can dampen their objects or systems to help the system from collapsing, right? Because if the system is going to be externally excited at these frequencies, they are going to displace a lot. And if they're going to displace so much, they're going to structurally weaken or collapse the system. That isn't something you want to deal with as structural engineers. So you study these different frequencies to avoid these different frequencies or to dampen these different frequencies, to prevent the object from naturally displacing, right? So that is why we study the first six modes usually. Usually the first six mode covers more than 90% of the vibration. For a cantilever beam, the first two modes of frequencies are going to talk about translation. This is the translation in the z-axis and the y-axis. And the next two frequencies are also going to talk about translation, but we're talking about weaker translations once again in the z and the y-axis. The fifth mode is going to talk about torsional, which is a rotational mode of movement. And the last frequency, the uh, the object, the cantilever beam, is going to axially move. It's going to compress, right? Compress in and compress out. So these are the six ways in which the cantilever is going to move in the first six frequencies. And they are going to move in different strengths or modal mass, which we're going to explore in just a second. But this is what I wanted you to understand, right? Now, when we click on this study option here, and I'm going to click on the compute button, it's going to take a minute, but then it is going to help me visualize the different modes I talked about. How I told you that the first two are going to be translations, the next two, once again, translations, but a little more weaker. Then I told you that the third mode, that's the fifth mode, is going to be torsional in nature. It's going to twist. And the last is going to be an axial movement where it compresses or it expands, right? Um, Now you see, this is the first mode, and you see that these frequencies are repeating. And the reason in which the first two, the third and fourth are repeating, we call this phenomena modal degeneracy, right? And you see modal degeneracy here because our cross section, right? You see our cross section here is symmetrical. It's point 0.1 and point 0.1. If our cross section was not symmetrical, then these modes would have been different. But since our cross section is symmetrical, you're basically seeing different values over here, the same values over here, sorry. You see that the first mode here, as I plotted here, is going to vibrate in the z-axis. But when I plot the second mode, you see it's vibrating in the y-axis, right? Instead, now the third mode is going to vibrate in the z-axis again, but it's slightly more weaker, as you can see. And the fourth mode is going to vibrate in the z-axis, and it's slightly more weaker. The fifth mode is going to be torsional, that is, it's twisting, as you can see here. And the last and the sixth mode is going to be axial, it's compressing, right? So these are the six mode frequencies. In fact, you could also animate them to sort of visualize how it's happening if you want to. You see, it's axial, it's moving to and fro, which is what you want to see. You could also try and visualize other modes if you wanted to, but we will stop at this, right? Now to continue with what we did here, we have essentially explored different modal shapes. We have explored different RBMs, right? And how I've showed you the different RBMs is these different eigenfrequencies. These are also resonant frequencies, correct? And we have verified these first six modes over here. But what you want to verify now is you want to check the angular frequencies, and to do that you can click on the Eigen frequency study, which is already created here, and you see the different angular frequencies for different resonant frequencies, right? You might want to make note of this value because this is important. And what you want to do after that is you want to check for modal mass displacement. You want to understand how much mass of the material, cantilever beam in this case, is displacing in each vibration, right? And to do that, you can check in the participation factor. There's a lot of different things in the participation factor. Our focus is primarily in for these modal frequencies or resonant frequencies. There is going to be a participation factor in the z and the y. There's going to be a modal mass. You see there's modal mass displacement. You want to check the y and the z modal mass displacements of all the six modes. And what you want to also check is the modal mass rotation of y and z, right? So you want to check modal mass rotation of y and z and modal mass translational displacement of y and z, and you make note of them in a separate table. Once again, these things are very important. What you can also do is you can sort of also transform these values as an average. This kind of helps you sometimes. You can format them or concatenate them as well. By making them an average, you see, you go to global evaluation here. It helps you normalize the data as an average or transform the data as an average. You can click on average and you can click on integration, and this is going to help you understand the total modal mass displacement, right? This is really fun because you can simply go to the mass translation of y and z, and you see this is total mass translation including all the six modes, and you can see the total effective mass modal mass translation and rotation for the different modes, right over here. And these are effectively the sum, which is going to give you a total displacement number, which is always very helpful, right? You can do that in global evaluation if you wanted to. Once you've drawn these tables, what you want to do is you want to plot, right? And the way to plot is to go to results and you click on the 1D plot group, and in the 1D plot group you want to add a line graph. And what you want to do this time is you want to click on study 1, which is our eigenfrequency study, and you want to define the cut line like we did in the previous experiment. One end of the cut line is going to be in the fixed points middle face, and the other cut line is going to be all the way to the free end. What we're essentially doing with this is we're trying to extract the solution wherever the cut line is going to intersect, and I'm going to make sure that I'm checking for solid displacement, and I'm going to make sure that it's along this arc length. When I plot for it, I get a beautiful plot of different displacements for different frequencies, and you can add a label. The way to add a label for this graph is to click on the show legends option, and you see the different frequencies, and the different frequencies are having different displacements. So this is the graph you want to sort of model, right? With this, we have effectively done with our study. But what you also want to do is theoretically verify if what frequency you're getting is what is expected. And to do that, we utilize an equation called the Euler's-Bernoulli's cantilever beam equation. Now, this equation helps you estimate the resonant frequency at which the cantilever beam vibrates, right? This is the equation. If you look closely into the equation, you see a few terms. This term here is what we call as the modal constant. Now, based on different modes or resonant frequency, the modal constant is going to vary. Now, for the first mode or for the first resonant frequency, the modal constant is 1.875. For the second mode, it's 4.694, and so on and so forth. Right? We will only verify it for the first mode. When you substitute for all these different values, now one important thing I forgot to add here is the moment of inertia for a cantilever beam is BH cubed by 12, right? Which in this case and this configuration is around 8.33 times 10 to the power negative 6, right? This is my moment of inertia, and when I plug in for all the different values, that is for the first mode, that is 1.875 the whole square divided by 2 times 3.14 times the length, by the way, in this case is 1 meter, right? So 1 square times root of E is the Young's modulus. If you go above, you see there's an expression for E is the Young's modulus. As I previously told you, the Young's modulus is 200 uh, megapascals, right? So it's going to be power 9, and we're going to multiply this with a moment of inertia, which is negative 6, and we're going to divide this by the density, which is 7850 kilograms per meter cube, and the area is going to be 0.01 because the cross section was 0.1 x 0.1 meters, right? And when you solve for this, you will essentially get a first frequency around 81.536 hertz. But if you checked our simulation data, you notice that the value for the first plot was around 81.312. So there's some amount of variance. The variance is around, the variance is around 0.3% approximately. This is very acceptable. As you go for the further modes, you see that the variance increases. It goes up to like 5% or maybe even 10% later on, and the variance keeps on increasing. But a variance of 0.3% is acceptable, and you sort of verify that this frequency is what we have seen in the simulation as well. So that is how you verify for eigenfrequencies. I think this concludes our study for eigenfrequencies. In the upcoming video, what we are going to do is we are going to study for a micro-cantilever structure, because so far we've been doing macro-cantilever. So I want to introduce a micro-cantilever, and I will also try introducing a parametric sweep, right? Because all so far I have been using a given configuration, and we're basically taking a snapshot of that configuration using static analysis, right? But when you start using a parameter, you can do a parametric sweep to take multiple snapshots by varying a single variable across different values, right? This is going to give us a relationship between that variable and different physical parameters, and that's very useful to, let's say, study how different forces will affect different displacements, right? We expect it to be somewhat linear or maybe slightly higher order. We will see how that's going to work, but parametric sweeps are very useful. I'm going to introduce this to you in the coming experiment with the macro cantilever, and hopefully in this demonstration you learned a thing or two. If you have any feedbacks, you can let me know, but otherwise I hope that you're having a nice day. Take care. Bye bye.